Hello, everybody. Welcome to this month's Rockin' Pop-Up with the Santa Cruz Museum of Natural History. My name is Marisa Gomez. I'm the Public Programs Manager for the museum, and I'm joined by the Geology Gents, Gavin and Graham. As always, we're going to be talking rocks today. Before we get into the program, we did have a special announcement that we wanted to start with, and I'm going to let Gents do the honors of sharing what that announcement is.
Yeah, hey Marisa. So as folks who have been keeping up with us probably know, we are in the midst of a three-part series, kind of looking at Earth's context in the solar system. But so this week we'll be talking about this month we'll be talking about the giant planets. Next month we're going to kind of talk about how the solar system formed, and that's because we're going to be ending with the beginning.
That's right, Graham. So we're gonna be doing our last virtual Rockin' Pop-Up, which will be next month. We've been doing these for 2 years now, and me and Graham are gonna transition back to in-person stuff, not do the virtual ones anymore. So next month will be our last virtual pop-up. It's been a good run though.
Yeah, it's been a great run. I mean, Gavin and Graham, they started volunteering with the museum 4 years ago. In April of 2018 was our first in-person program with you two. And you did 2 years of in-person programs with us before transitioning to virtual when the museum closed in March of 2020. And we all know why. And so you quickly transitioned and helped us out with getting started with virtual programming. We've been doing it for 2 years. And so next month in April is going to be the 2-year anniversary of that transition, the 4-year anniversary of your relationship with the museum. And so we're going to wrap it up with a nice bow with your last Facebook Live virtual Rockin' Pop-Up, but it's not the end. For instance, Gavin's going to be leading a walk with us this month in March, on March 12th. Exploring the geology of West Cliff Drive. I'll drop a link to register for that in-person program in the chat. There's going to be other opportunities like that going on, but we are going to take a break from doing these. So enjoy them while they last. And on that note, I'll hand it over to you guys to share what you've prepared for us this month.
Perfect. All right, let me share my screen.
Yeah. So Gavin, while you're getting the screen shared, where are we right now?
Well, Graham, we are pretty far from home. We're on the surface of Europa. So what is Europa? Where are we, Graham?
Oh my gosh, Europa, that's one of the Galilean satellites of Jupiter, which is the biggest, the baddest of the planets in our solar system. And it's cold out here, Gavin. It is freezing out here. So I think we need to warm ourselves up by talking a little bit of planetary, not Earth, but planet extraterrestrial geology.
Yeah, that sounds great, Graham. The views are nice, but you're right, it's cold. So we're talking.
That sun is looking real faint off in the distance.
I know. So we're talking giant planets. As we said, this is part 2 of our our solar system focus series. And so without further ado, there we go. This is our planets. Start there. Last week we talked about the terrestrial planets. Graham, those are the rocky bodies, right?
Those are the rocky ones. Yes. Planets like Earth, ones that we know kind of well. Planets where we could look at the differences between them and Earth, but when you really zoomed out in an astronomical context, really gosh darn similar,
Yeah, it was super easy to make the comparisons, right? We're like, oh, they're all differentiated, they're made up of this stuff or that stuff, but you're right, very, very similar when you put a more general lens to it. But these planets we're going to be looking at today, Jupiter, Saturn, Uranus, and Neptune, those are quite different, huh, Graham?
That's right. And when we look at this picture here, this is a nice way of just comparing them in terms of size, right? And that stands out, right? They're very, very different in terms of size. but also in terms of our solar system geography, if you will. We're in an entirely different space. You know, those terrestrial planets are tucked in, warm and cozy around that bright sun in the center, but we have to go way, way out to start thinking. You know, we go over twice as far as Mars to get to Jupiter. And by the time we get all the way out to Neptune, we're 30 astronomical units. And astronomical units is just the distance between Earth and the sun. And so we're 30 times as far away to get out to Neptune.
The sense of scale is wild, right? Like, so the giant planets are cool because they're giant, but also there's so much more space in between them. And when I think about this scale, it's kind of fun to think like, you can see Jupiter and Saturn sometimes in the night sky, like you can see faint dots of the planets. That's just a testament to how big they are, because they're pretty far away, but you can still see them in the night sky. It's pretty interesting. And so, yeah, definitely the sense of scale in the solar system is pretty neat. And as we said, right, the sense of size in the giant planets is also kind of neat and something we'll touch upon today, right, Graham?
Definitely, yeah. I mean, we've got these enormous ones and then some that are not Earth-size, but getting closer.
That's right. Okay, so with that, let's jump into it. We threw this slide in here again just to remind everybody of our Earth-like lens, right? We look at every other planet and in a comparison, if you will, of between Earth and that planet. And as we said, these planets will be very, very different. But Graham, you want to just give us a quick spiel on Earth to remind everybody?
Yeah, I would love to. This is something nice and familiar in terms of planets. So our Earth, we've got this rocky mantle that is sitting over a metal inner and outer core. Our outer core is liquid. As that moves around, that's what gives us our magnetic fields. That's why magnets are used in compasses. That protects us from all this nasty radiation from the sun. But what's really cool about Earth is that we've got this rigid crust. And that rigid crust is made up of plates, and those scoot around, and those make, help us have things like oceans and mountains and continents. And then on top of that, we've got this lovely atmosphere that keeps us alive, with water in all three phases. And ain't that just a beautiful thing, Gavin?
Oh, it is the stuff of life, Graham. And so, so again, we are on a terrestrial planet. It is made of rocks, primarily solid rocks, and most of the liquid and gas on our planet is made of water. And so that's going to be a really good starting place, because the giant planets are not like that. Not like that.
That's right.
So I guess with that, let's start looking at the giant planets. First, in terms of the inner workings, Graham. So here we have the size of Earth, and this is to scale. So Jupiter, Saturn, Uranus, and Neptune, and we're looking at a cross section. So can you take us through this first part, Graham?
Yeah, absolutely. So the only thing on these planets that would feel really at all familiar to us is going to be their rocky cores. Their cores are the only parts of them that have rocky metallic stuff, the kind of stuff that Earth is made out of. And that's essentially, the core of Jupiter. The cores of Jupiter and Saturn are about the size of Earth. Maybe I don't remember exactly if they're a little bigger. One of them might be a little smaller, but that's about an Earth-sized thing. It's just the cores of those. But Jupiter is about 11 Earths across, and so it's huge. And so layered on top of that core, Gavin, there's something that we interact with very infrequently on Earth. What is the most of the stuff around that core?
Yeah, this gray part here, that's metallic helium and hydrogen, or mostly metallic hydrogen. So yeah, as you were saying, Graham, really the only thing that's familiar to us is the core here. The rest of this mass of this planet is all liquid and gas. The only solid thing is the core. So it's sort of a hard, counterintuitive way of looking at stuff that makes a planet, but think about all of the stuff that makes up Saturn and Jupiter as helium and hydrogen, and depending on where they're where they occur in the planet, that sort of dictates what phase they are. So when we see the outsides of Saturn and Jupiter, what we're looking at, right, the textures we're looking at, we just see their atmosphere. They have incredibly thick atmospheres of hydrogen and helium. But because their atmospheres are so thick, you reach a pressure barrier in the composition where instead of being a gas, that hydrogen and helium molecules are actually forming like a metal. It's acting like a liquid though, right, Graham? It's not quite solid like metal we think about.
Yeah, and you know, it's a phase that it's, you know, we think of our solid, liquid, and gas, you know, ice, water, and water vapor. You know, it's a different sort of process that's going on there. And you know, the ways we think of hydrogen, you know, hydrogen is we rarely interact with hydrogen in our day-to-day lives. It's a constituent of water. It's this very light, you know, atom or molecule in the case of the upper atmosphere. So if you could pop to the next slide, Gavin, that should have a legend for us. Yeah, that helps orient ourselves. And so, yeah, that outer part, you know, that's hydrogen and then helium, right? The stuff we usually think of in balloons, like something both of those are very scarce in those phases on Earth. And then yes, once you get under enough of those pressures, those hydrogen molecules kind of split into this metallic fluid like stuff that is, you know, we wouldn't be able to recognize, and it wouldn't matter because if we got that deep inside of the planets, we would be squashed.
That's right. Yeah. And so a little aside there, the reason we characterize this as acting like a metal is actually because it conducts a lot of electricity as it moves, right? It's moving like a liquid, similar to our like outer core, you can almost think about it. But these large planets have really, really strong magnetic fields because of this metallic hydrogen and helium on the inside. Yeah. But Graham, do you want to take us through why the gas giants are different than the ice giants? Why Jupiter and Saturn are different than Uranus and Neptune, just in terms of like their inner composition?
Yeah. So Jupiter and Saturn, when you look at their atmospheres, their gassy envelopes, it's almost all hydrogen and helium, very nearly 100%. When you go to Uranus and Neptune, it's not just hydrogen and helium. You're seeing a little bit more water. You're seeing nitrogen. You're seeing sulfur and oxygen. You know, they've got some heavier elements in there. You know, Jupiter and Saturn are pretty close. They're not exactly the same, but they're pretty close to just the stuff that kind of makes up our sun. Whereas Uranus and Neptune, you know, something else happened kind of there. It's not just that they're smaller, it's that they got some heavier elements in there that are mixed into their gassy envelopes.
Right. I like that, Graham. That'll be a good jumping off point. So for folks who are viewing, if that all sounds like a lot of information coming at you, we will now break down each of these 4 giant planets individually so we could take a little bit deeper of a dive and explain a little bit of what we just started with.
Sounds great.
Oh, I forgot though, Graham. These are also different from Earth in that they've got a lot of moons. The moons are noteworthy in this part of the solar system, right?
Absolutely. And hopefully we can take a moment by looking at these moons and see something a little bit more familiar, right? We were just talking about thick envelopes of hydrogen and helium, metallic hydrogen that conducts electricity. Ooh, frightening stuff. But things that are a little bit more Earth-like are the various moons of these giant planets. And golly, are there a lot of moons. This is just a small selection. And you can see here that, you know, these are a little bit more Earth-like. And some of them are even moon-like in terms of our Earth's moon.
Yeah, and Graham, you're right in that because they're Earth-like, these have been a really primary target for scientists in terms of understanding parts of the solar system, right? Because one of the things that NASA and space agencies are always looking for are Earth-like planets that could harbor life as we know it. And the giant planets aren't that. They're so different that the life as we know it, the carbon-based life, would not survive in the slightest bit on the giant planets. But their moons, as you said, might actually harbor some forms of life. And so we'll jump into some of the most noteworthy moons, especially for Jupiter. But it's important to note Jupiter has 80 moons, right, Graham? And Saturn has like 70 something like that. So there are a lot of moons around these giant planets.
Yes, lots of them. We'll focus on some of the really famous ones and the biggest ones, but definitely will not have time to cover each and every one.
Right. Okay. So with that, we are looking at the gas giants.
Yes.
And Graham, these are the two largest planets in our solar system. We said that they're made up mostly of helium and hydrogen. And so do you want to take us through like some of the distinguishing features here about the gas giants?
Yeah, so like we said, mostly helium and hydrogen, and you can see they've got these bands on them, these big, cloud networks. And right, what really stands out about these is it's their composition, which is they're just so big. So Gavin, how did these things get so big in the first place?
Yeah, that's a really good point, Graham. They're big, and most of their composition most of their mass is made up of gas. And so when in the early solar system, these things were in a part of the solar system beyond the frost line. So they can actually pull in gases and keep those gases instead of having those gases volatilize off. So that's one really important part of this, that these large planets outside the frost line are able to capture gases and keep them inwards. Keep them as a part of the planet. You also, as we said, the gas giants, Saturn and Jupiter, have huge cores. And so those cores allow them to exert large amounts of gravity and allow them to capture a lot of that early solar nebula stuff. So that solar nebula in the beginning is hydrogen and helium, and they're able to capture that hydrogen and helium and keep it within the planet.
That's right. Yeah. And so we'll talk about a lot of this in our next month's pop-up, where we talk about the sort of earliest stages of our solar system when the Earth first formed, and all this other stuff formed. But right, we're forming out of this collapsing cloud of mostly gas and a little bit of dust. And so inside of that frost line or snow line, things get hot. You bake off hydrogen and all this light volatile stuff, as we call it. But outside of it, it's chilly. Most things are staying condensed together. And that's how you can start putting these big planets before them. And you can get these big planets to form. And just like you said, Gavin, once they got a big enough core, these things were just gobbling up gas and dust and could not be stopped.
That's right. That's right. So if folks remember from last pop-up, we talked about the fact that Earth formed inside the frost line. So most of its volatiles were volatilized off. So that's just a little bit of a reminder there. So these are further away outside that frost line. Okay, so with that, let's jump into our first giant planet, Jupiter. And this is a very picturesque planet, Graham. Like, what are these stripes? And I like this GIF you put here. What is going on here? What's this thing? It's a big red spot, right?
That is a big red spot, and that's actually what scientists call it. So to understand the big red spot, we need to know what these bands are. And these bands should be pretty familiar to folks who've tuned in for our Motions of the Oceans and Atmosphere episode. These are just these like weather gas, atmospheric circulation cells. So they're much like the Hadley cells we've talked about before, of gas getting warm and rising and falling, and it makes this sort of latitudinal stripes around the planet that of moving gas. And the great red spot fits in there because it is a storm, and it is a storm bigger than Earth. All right, you've got this huge storm in the atmosphere of Jupiter, bigger than the size of planet Earth, and this thing has been around for a hot minute, right, Gavin?
Yeah, this is a really old storm. It's just like, I guess it's a testament to like the forces on the surface of Jupiter and the time scale with which those can operate. So this storm is at least 150 years old, So it has been storming. That is a long storm. It's been
It's a very
storming
long time.
years. Yeah.
But it has also been shrinking lately. So who knows? We may be seeing the end of the Great Red Spot. I don't think it's going to be gone anytime soon, but it is. It's this big dynamic storm. It's been around for an incredibly long time. Yeah, it's once again another one of those things that's kind of hard for me to wrap my head around. We had a snowstorm here last night out in New Hampshire, and I was like, wow, this is going on a while, but not 150 years long.
Imagine that. Yeah. So again, Graham, these bands are basically your trade winds. And so this is a cross section of that. You have these circulation cells that form it as latitudinal bands, very similar to how the Earth's trade winds work. Then another interesting part of this, we talked about how these planets have very, very, very strong magnetic fields. So can you explain what we're looking at here, Graham?
Yeah, those are the northern lights, or the aurora borealis of Jupiter. So just like how Earth has a magnetic field, Jupiter has one too, churned up by that metallic hydrogen outer core. And so it makes the same sort of ionizing good stuff that makes a set of northern lights. And so, you know, there are still some similarities between Jupiter and a planet like Earth. And the other thing on the slide is there's an image of the Juno orbiter, or the Juno probe, which has been and continues to collect a bunch of awesome information about Jupiter, and is part of how we know, you know, most of what we know about Jupiter today, by being able to get close up there and make some of these, you know, important measurements.
Right. And this was a flyby, right, Graham?
Yeah, and I think it's still orbiting now.
Is a flyby. It's an orbiter. Got it. Got it.
Yes.
Got it.
Yeah.
Cool. One thing that we did last pop-up was think about the days and years on these planets, and it's cool to look at that on these big planets too, because if you remember back to that slide we had about showing the orbits of these planets, a year must take pretty long because the orbit is so big that it takes takes a much longer time to orbit the Earth one time, which is a year on Earth. So as we can see, the year on Jupiter is 12 Earth years. So makes sense.
Long
what
time.
About
Yeah, and so these planets are spinning a lot faster than, or you know, not a ton faster, but significantly faster than Earth does. It only takes 10 Earth hours for a day to pass on Jupiter for it to spin all the way around. So yeah, moving a lot more quickly.
Yeah, that's interesting. So spinning about double the speed, but orbiting at a much slower pace.
Yeah, that's right.
Okay, what is that all oh yes, the moons. I keep forgetting about the moons.
Yeah, I know. How dare you forget about these lovely moons? Yeah, so over here on the left, this is a transit of several of the moons. So you can see their shadows over the planet. You can see the moons over them. And the awesome thing about these moons is that you can see them through a telescope. They're called the Galilean moons because Galileo was the first person to see them through a telescope and, you know, start thinking like, gee, what are these? Are these moons like Earth's got? And so, yeah, and so both of these images kind of show what their size is like relative to Jupiter.
Yeah, pretty interesting, Graham. And as we said, Jupiter's got 80 moons, but because these are the biggest, these are the ones we can see. And so Galileo in the 1600s was looking through telescopes and looking at these, and you can do that as well. So each of these moons has something different and unique about it. Io is one that's very unique in terms of celestial bodies because it is both the most geologically active moon and also the driest place in the solar system. So it's got over 400 volcanoes, the most geologically active in the solar system, as I said, but also the least water. So this is kind of a weird sort of place, right, Graham?
Yeah, this is a wild place. The other ones, Europa, which is that next one down from the top in that image on the right, that one is famous for having a massive ocean. Of course, on the surface, it's frozen, it's ice, but there's a big ocean underneath that. And folks often think about these ocean worlds like Europa as potential oases in our solar system for life to survive.
Right, right. We then have Callisto, and Callisto is a little bit of an outlier here. It's the only one of these that isn't fully differentiated, and so it doesn't have a defined core mantle, like we think about it. It might have a silicate core, but it's not quite fully differentiated. It is, however, made of basically like equal parts silicate and ice. And then the last one being Ganymede. Do you want to take us through that one, Graham?
Yeah, and Ganymede's cool because this is the biggest moon. It's the 9th biggest body in the solar system. So this is the biggest of all the satellites. And I am blanking right now, Gavin, on some of the details, but I think it's kind of similar to its friends. It is watery. It's got a mix of ice and rock. And other than that, yeah, its big claim to fame is it's a jumbo moon.
Yeah, definitely. That I would say you about summed it up. It's in terms of composition, Ganymede is a lot like Callisto, basically just silicate and ice. But yeah, the really identifying feature is just how big it is, the biggest moon system by far. So we did it. Those are the Galilean moons, and so some of the highlights. Okay.
Awesome. And of course, Jupiter doesn't just have moons. We'll talk about rings in a little bit. Jupiter has very minor rings, but Jupiter is rather aptly named after the king of the gods, Jupiter or Zeus in Greek, because Jupiter really kind of runs the show especially around its neighborhood in the solar system. So the asteroid belt exists because Jupiter's gravitational pull is so strong, it would tear up any planet that tries to exist in that zone. And because of the huge gravity of Jupiter, and of course the huge gravity of our sun, Gavin, Jupiter's got a set of groupies that hang along with it. Tell me about them.
That's a perfect way of putting it, Graham. Yeah, so Jupiter just like pretty much calls the shots in terms of how things are oriented in the solar system. Because you're right, it's so big, it has so much gravity to it. So when Jupiter's gravity interacts with the sun's gravity, it creates these sort of like gravitational low areas. And in those areas where you have the two gravities interacting, you get a bunch of asteroids building up. So there are also these two asteroid belts that are in the same orbital plane as Jupiter's orbit. And they sort of stay 60 degrees away from Jupiter at all times. And these are called the Trojan asteroids. And there's actually the same amount of asteroids in these Trojan asteroid belts as there is in the main asteroid belt. So this is like a whole sort of phenomena that is brought to pass because Jupiter just has so much gravity.
Wow, incredible. Well, I'm impressed. Jupiter, bravo.
I would agree with you. It's aptly named. But what about the other giant planet? Because Graham, Jupiter's cool, but I think Saturn probably is the most famous because of its rings. Right?
Oh my gosh. Certainly Saturn wins the beauty pageant, I think. These rings are absolutely stunning. And so yeah, when we take a look at it, we can see, it's not as defined as on Jupiter, but it's got clouds, it's got these bands on it. You've got, a pretty similar sort of weather system, not quite as pronounced, but really that just pales in comparison to this huge, well-established ring system. It's got tons and tons of moons. You can even see a few of them in this image here. There's one up over it. I think there's even a moon down in the bottom left-hand corner as well, a larger one. Yeah. And this thing, it's spinning about as fast as Jupiter, but it's way further out. It's got 30 Earth years or 29 Earth years. Wow. Yeah. What a beauty.
Yeah, it is. And you're right, Graham. In terms of composition, mostly hydrogen and helium, just like Jupiter. We showed you the cross sections before. in terms of the interior. But just like Jupiter, it has a pretty large rocky core. Then you have that metallic helium and hydrogen layer and that gaseous helium and hydrogen atmosphere. And so, yeah, very, very similar in terms of Jupiter, a little bit smaller, but the rings steal the show. So we might as well talk about them for a little bit, Graham. This is just to get everybody oriented. We're looking from the bottom of Jupiter up at its rings. This outside ring counts as a ring. And this is sort of a top-down view of the ring system. So what we should say first is that every single one of these giant planets has a ring system, but the only ones that are complex and visible are Uranus and Saturn. And Graham, take us through. These are some like pretty complex ring structures through here.
Yeah, and so these rings aren't actually a single solid mass. They're made up of a bunch of dust and debris, rocky, icy, this awesome sort of solar system mix that you can find in the outer solar system of ice and rock all mixed up together. And so there's so much of it, and it's so kind of intermingled that it looks like these solid rings. But yeah, you've got these layered rings out, but then you've got gaps in these rings. And Gavin, who's interrupting the ring system here? Why isn't it all just kind of one continuous ribbon?
Yeah, that's a great question, Graham. And it actually turns out to be like a somewhat complex question. So the most prominent gaps are gaps there because they're sort of disrupted. The orbits of this icy and a little bit rocky material is disrupted by moons. So that's often why you get the big gaps. Not always, though. Some of the gaps are other disruptions in terms of the orbit of these rings. But you can also see that there's a gradient here. And as you get further out, you get less dense. And so there's a gradient of density within these rings too. And so both the formation of each ring and what they're made out of differs. And so this is actually a pretty complex system that gives Saturn's its rings.
Awesome. Yeah, and rings with little moonlets tucked inside. I love it.
That's right. So Graham, I like that you brought up moonlets because that's a perfect transition. So again, we said that Saturn and Jupiter both have lots of moons. One of Saturn's moons actually usually steals the show though, and that is Titan. So Graham, you want to take us through Titan? Why is Titan so cool and something that scientists are excited about?
Yeah, so Titan's awesome because it's the only moon with a substantial atmosphere. And in terms of atmospheres, it's kind of similar to Earth because it's mostly nitrogen, and Earth's atmosphere is mostly nitrogen. However, it's too cold for any liquid water or water vapor like on Earth. And so instead of water vapor, it has methane and ethane. And so it's got these really kind of simple alcohols that are very toxic to any sort of terrestrial life, but it has clouds and rains of methane. It has methane or ethane lakes. And so you get the same sort of landforms that you get on Earth: rivers, deltas, dunes, lakes. And so, there's also even probably these like icy cryovolcanoes on the surface from ice that melts in its so water ice that actually melts in its deep interior. So because it's got all these things going on, folks think it might be an oasis for life, but it might be life that's chemically very different from us, that doesn't use water and oxygen, but uses ethane and methane.
That's so cool, Graham. So basically, like, instead of a water cycle like we think, where we have water in oceans, it evaporates, makes clouds, that rains out onto the continents, this has similar things going on, except it's methane and ethane, which are alcohols that are, I wouldn't want to drink them nor swim in them.
Oh, goodness, no.
And something really cool is that the surface, which is solid ice, also shows very similar features to like the surface of Earth and pretty much Earth, right? You have these, I was going to say the moon, but these things are not things you would see in the moon. So
that's true. Although we've hopped to a different satellite here. This one's Enceladus.
Okay. Thank you, Graham. I didn't.
Yeah, sorry. I should have mentioned that.
Cool. Okay, so this is Enceladus. So talk about Enceladus here for a second.
So Enceladus is kind of like Europa's Saturnian sibling. It has an icy shell. There's a salty ocean beneath that. This is another one of those ocean worlds that might be an oasis for life. But yeah, like Gavin, just like you pointed out, it's got these sort of wrinkles on it, places where you can see that this crust is changing with time.
Yeah, definitely. And so this is basically like tectonic features in the icy crust. You also
Yeah.
is in the poles where it's got a lot of craters, so very
Mhm.
similar things as you would see. Another really cool thing about Enceladus that I'm always like mind blown about is that the brines that are liquid deep inside of Enceladus oftentimes make their way to the surface in geysers. So if you look at the edges of Enceladus, you see these like briny geysers shooting out of the middle of it. It's pretty wild. Pretty.
That's so cool. And then the last thing to talk about with Saturn is that, it might still be making new moons. If Gavin's got the cursor right over this little lump in the rings that was imaged, like in the 20 teens, and has been hypothesized as maybe a new moon forming out of the rings. So we'll certainly be interested to hear how that all pans out.
Totally. Yeah. So again, moons are really wild in this area of the solar system. A lot to still learn about them and even explore. So these are definitely good targets for orbiters or maybe even landers one day to go out and explore these places. So those are the moons. Those are the gas giants, Graham. But we would be remiss if we didn't talk about the ice giants. They're also giant planets, smaller than the gas giants. And tell me why they're distinguished. Like, what is it that's mainly different?
Yes. So despite their name, they are not particularly icy. They are very gassy. They have mostly hydrogen and helium in their outer envelopes, their outer gassy envelopes, but they've got a lot more heavier stuff. They've got things like methane, they've got things like water, they've got these heavier elements, oxygen, sulfur, nitrogen, that are a little bit more incorporated in there. And folks think that those were probably sort of brought in by ice when they were first coming together. And that's how they get their rather misleading ice giant name.
Right. I remember when I learned that, I was like, wait a sec, why are they called ice giants? Solid ice on them. But you're right, Graham. It is a compositional thing. It's that unlike the gas giants, which their cores were so big, they were able to capture that really primordial gas in the solar system. These planets aren't capturing as much gas, but they're still able to capture heavier volatile elements based on where they are outside of that frost line. So they still are very big, just less big.
Yeah. All right. Well, let's dive in and look at the next one out from Saturn, Uranus. And so, yeah, Gavin, you mentioned it's got this really beautiful ring system. It's harder to see than Saturn's, but if you catch it in the right light, it can still show itself off. You can see that there's bands around there. They're in a different direction than we're used to, and we'll mention that in the next slide. But then, yeah, you can see circulation, you can see clouds. We're seeing some familiar things going on.
That's right. Yeah, Graham. So just like the large planets, or not the large, these are all large.
The larger planets.
Just like the gas giants, what we're looking at here are thick atmospheres. So on the surface of Uranus, you still have a pretty thick atmosphere made of, hydrogen, helium, maybe some more like heavier elements. But Graham, I think when you put the slide together, you flipped them on their sides. This is looking a little bit backwards, or is this right?
Gavin, this is right. At some point in its history, Uranus, right, we're used to planets that are rotating like this. It got flipped. And so it is always rotating like this. And so this makes for some wacky seasons on Uranus over the course of its 84 Earth year and trip around the sun. So Gavin, tell me what's going on in our summers and winters here?
Yeah, this is a super interesting thing, as you said. So again, its rotational axis is on its side, so it's spinning like this instead of like a top. And so you can see that when it's at its summer solstice and winter solstice, you have basically completely dark times, right? There's no actual days during those times. Whereas when it only has days, right? It only has changes in light based on the rotation in its autumn equinox and its spring equinox, when that rotational axis actually allows it to allows days to change on the due to the rotation. So when it actually does have days, those days are about 17 Earth hours. So it's still spinning a little bit faster than Earth. But the real weird part is that it's spinning on a totally different axis.
So strange.
Yeah. Yeah, but as you said, 84 Earth years. So we are getting further away from the sun. And as we get further away from the sun, it takes longer for these orbits to complete one orbit. So Graham, that's about all for Uranus. We don't know too much about these ice giants, so there's less information to jump into. But so let's go to Neptune, and this one is doesn't have the weird rotation, doesn't have the weird rings, but you can still see some interesting stuff going on in its surface. You want to take us through it?
Yeah, so Neptune is a stormy planet. So you can see that all over it, you get these sort of darker marks on the body. They're spots, just like the Great Red Spot. And so in the two images to the left, there's that big sort of oval shaped thing that was called the Great Dark Spot. But several years ago, it just disappeared. It went away. And in its place, a new spot has plopped up in the northern hemisphere that's now called the Great Northern Spot. And so it can't be as long-lived as the Great Red Spot on Jupiter, but we've got these big, long-lasting storm systems on Neptune that kind of hop around some.
Yeah, it's super crazy because they're still giant storms, and kind of interesting to think about like the life and death, or the birth and death of a storm like this, Graham. It's like the Great Red Spot seems to have always been there, but it would be really neat to see one of these storms sort of die and another one pop up. So we can do that on Neptune. It's kind of a neat place.
Yeah. And I also think it's neat that Neptune's got clouds that actually look a little bit more familiar.
Yeah, here's one right here, right?
They're probably made out of things like methane, and not so much the water vapor that we're used to, but it's kind of cool to see these, more familiar wispy looking clouds on such a different planet.
Definitely. So, but in terms of composition, very much like Uranus. So the two groups, the ice giants and the gas giants, both have very similar compositions to themselves or their partners, but different compositions between the gas and the ice. So again, Neptune is probably very similar in composition and an internal structure as Uranus.
Yeah, absolutely.
So Graham, we talk about our giant planets in our solar system, but these are not the only giant planets that exist in the galaxy or universe. And so we also are over the past, what was it, 20 years, Graham, mostly in the past 10 years, we're discovering exoplanets at a crazy rate. So can you just define exoplanet for me?
Yeah, so an exoplanet is a planet that's around a star other than our own sun. And so none of these are actual pictures. No one, there aren't, nice colored photographs of exoplanets yet, maybe one day. But yeah, these are some artist concepts of what these ice and gas giant exoplanets might look like. The Jupiters and Neptune-like planets of other star systems.
Yeah, and you're right, Graham. This is a little bit of science fiction. We don't know what they look like this, but when we discover them, they're basically like blips on a telescope map, right?
Yeah, that's right. They're usually being measured by sort of abnormalities in the way that their star appears through a telescope. So it might be that the star dims out a little bit as the planet passes over it, or it might be that the star wobbles a little bit in a way that it shouldn't. And that means that you've got a planet tugging on it gravitationally. And so There are a few cases where folks have been able to sort of image really young planets, but mostly we're just seeing the changes in the stars. And those easiest ones to see are what we call hot Jupiters, because they're really close to the star, so they can kind of wiggle it a little bit more. They cover up more of it. And so we call them hot Jupiters, not just because they're so good looking, but it's because they're so close to that sun, or they're so close to their star.
That's right. That's right. So these are gas giants like Jupiter, so we can compare them to Jupiter. But because they're so close to the star, as you said, they're hot. And because they're so hot, they're losing some of that gas. So they have a little bit of a tail, like this GIF you show here.
That's right.
Yeah. So I was just going to say, Graham, these are also the easiest exoplanets to see, right?
Yes. And so early on, folks used to think that most other planets were hot Jupiters, but it's probably just because those were the easiest ones to see. So we were able to spot a lot of those. But now we're starting to see a whole menagerie of other types of exoplanets, including Earth-like exoplanets that we talked about last time, things like these hot Jupiters, different flavors of Neptune-like planets out there. So we're really finding quite this planetary zoo out there.
Totally. Yeah. So these are some of the, again, artist renditions in terms of color and maybe even texture, but real exoplanets that we've seen and named. So WASP 12b being one of them. And so there, as you said, there are several of these. A lot of them are like the gas giants and like the other giant planets, but there are some that sort of fall in the middle, right?
Yeah, and that's what's super cool about some of these exoplanet studies, is that we're finding planets that aren't just gas giants and ice giants, that aren't just terrestrial earthy planets, but things that are falling kind of in the middle of those. And that, I think, is, an exciting thing for just learning about, how different the various Earths out there might be.
Yeah, totally. It's kind of neat too, Graham, because one of the themes of these two last pop-ups was that the way the planet is, the way the planet acts, the way it looks, the stuff it's made of is really a function of where it formed in the solar system and when and how rapidly. And so it kind of makes sense that not all other solar systems are going to have exactly Neptunes or exactly Earths. There are middle grounds, right?
That's absolutely right. Yeah.
Well,
a little this and a little that.
That's pretty cool. I like that. It gives me
Yeah.
sort of a lens to think about the wider types of planets that exist in this massive universe. So kind of cool.
Absolutely. Very exciting to think about.
Well, with that, Graham, do you want to talk about our final Rockin' pop-up?
Yeah, so we will be finishing out our solar family trilogy. We'll be thinking about the sun, the center of it all, the asteroids and the comets. But what I think is going to be the most fun part with that is that those are what we know by studying the sun, the asteroids, and the comets. Those actually tell us a lot about how the Earth formed. So I'm kind of excited that we'll be ending by thinking about the beginning of our planet.
Totally. And it's going to be really cool. You're also not an unbiased source on that because that's what you're doing your postdoc on, right, Graham?
That's right. That's right. I am thinking all about how planets form right now. And I think that's all super, super rad stuff.
Well, cool. I'm looking forward to it. That should be good.
Me as well.
Yeah. Coming to an end, but not really. There will be plenty of other things. As I mentioned, we've got a walk with Gavin coming up. We'll come up with other things too. And Gavin and Graham will also continue to be able to be resources for identifying rocks. So I know we've gone a little long on today's program, but I wanted to close this out by just sharing a submission that we received. Someone found a rock or a fossil near New Brighton Beach and wanted some insights. So I'm going to share my screen and just show off this particular specimen and see what you two think we're looking at here. So they took pictures with a ruler, which is great. I'll show some different angles.
Yeah, look at that.
Wow. And I can see why, this has been suggested as a fossil. You've got these kind of like limb articulated sorts of things. But gee, Gav, I don't know. We did get a moment to take a quick peek at this and discuss it a little bit. And I think Gavin gave a great synopsis. So I'll let him take the spotlight here.
Yeah. As you said, Graham, there are things that look fossil-like, but oftentimes when you have a piece of rock, a hand sample of rock that's highly weathered, it weathers in these distinctive patterns that have to do with its composition or just the textures within the rock. I think that this is actually a weathered metamorphic rock. It's highly weathered. And the reason I say it's metamorphic is because I see some parts of it that look like serpentinite. So these sort of fibrous-like textures in here. Marisa, if you pop down to the next one, I think you could also see it, or the last one maybe. Yeah, you can see it in all of these three last ones. But yeah, these textures and the color make me think serpentinite. So what I think is happening is that I'm not quite sure of the composition of the parent rock that was metamorphosed, but you have serpentinization going on in this rock. And based on the overall texture, the sort of knob-like features, I feel like it's very, very highly weathered, perhaps both physically weathered, like broken down, but also chemically weathered, because it's got like, this like reddish tint to it. So I think, this is a weathered metamorphic rock, if I had to say.
Yeah, it's interesting because it was found near New Brighton Beach, which is where you find fossils in this area. That's like one of the best places for looking at local fossils. So I can see why, another reason why one might assume, just in context, but that's interesting. So how would it have gotten to New Brighton Beach if it's a metamorphic rock?
Yeah, so as we've talked about a bunch in terms of serpentinite, the coast of California is just rife with the stuff. A lot of the coastal rocks of California, as you go up and down, especially as you go up north, are Franciscan melange, which is basically all of the sediment that was scraped off the downgoing slab. And so it's sort of like just a hodgepodge of different types of rocks, but there's a lot of metamorphism going on because there are a lot of hot fluids that are moving through it. And so that's why you get a bunch of serpentinite in the melange. And if you look at the beaches, even in Santa Cruz, long enough, you'll find all kinds of different rocks that come from the mountain and just make their way to the beach over time. And so I'm not totally surprised that you see a rock like this on the beach, even though there's no obvious source of it close. These types of rocks can move over pretty long areas.
Cool.
Yeah, and these roaming rocks become, some of the gems of the beach that kind of stand out amongst the local rocks there.
Cool, great. Well, I'm glad we were able to answer that question. And even though we'll be closing this series and moving on to other endeavors, you're always welcome to submit things that you find in nature and see if the museum can help you out. You can email them to info@santacruzmuseum.org and we'd be happy to help you out. And we also have one more Rockin' pop-up coming up. So this is your time. If you want to hear from Gavin and Graham live into your home, then send us your rock questions over the next month, and then we'll see you in April for the final one. And on that note, I think we'll say goodbye until our next and final pop-up.